Hello, welcome to GP Podcast. Today we're diving into a story that feels like it's been pulled straight out of science fiction. But the thing is, this is happening right now, in our world. We're talking about the global race to build a quantum computer. Yeah, a machine with the power to change pretty much everything. And that race, well, it has just taken a very, very unexpected turn. For years, the world of quantum computing has been defined by this really strange paradox. While you have the titans of tech in the West, Google and IBM, being the public face of all this cutting-edge research, something else has been happening, very quietly and very quickly, on the other side of the world. And this isn't just some research paper. We are talking about China officially selling the world's first atomic-based quantum computer and locking in millions in overseas orders in just a single day. A critical line has been crossed here, from the pristine lab to the messy real-world marketplace. So what's the real mystery here? It's the stark contrast you're seeing right now. On one side, you have these incredible but unbelievably delicate lab experiments, and on the other, a commercial product that's already being shipped out to clients. How is this even possible? How did this happen so fast? To solve this puzzle, we have to go back to the beginning, to the one fundamental challenge that has kept quantum computing locked away in labs for so long. And let me tell you, it is a ridiculously difficult engineering problem. And it all comes down to this, the qubit. A regular computer bit is like a light switch, right? It's either on or off, a 1 or a 0. But a qubit is more like a dimmer switch, able to exist in a special state where it's both on and off at the exact same time. This mind-bending ability, it's called superposition, and it's the source of a quantum computer's theoretical power. Instead of checking answers one by one, it can explore a vast landscape of possibilities all at once. But here's the catch. That power comes at a huge cost. Qubits are unbelievably fragile. The slightest whisper from the outside world, a tiny change in temperature, a stray vibration, any electrical noise can instantly destroy the quantum state and just ruin the entire calculation. And this central challenge of fragility is exactly where the two sides diverged. They chose fundamentally different paths to solve the same problem. You could almost think of it as a classic tortoise and hare story. And this right here lays out that split in black and white. The West has largely bet on superconducting circuits. That's the hare approach. They're incredibly fast, sure, but they have to be cooled to temperatures colder than deep space, which requires these massive, energy-hungry refrigeration systems. But China's Hanyuan one, the tortoise, uses neutral atoms held in place by lasers, and this is a method that actually works at room temperature. And this different approach yields a machine that's not just a lab experiment. These numbers aren't just for show. That fidelity, which is basically a reliability score for the quantum operations, is high enough to prove this machine is a consistent, practical tool that's ready for real work. And get this, the entire system, the whole computer, fits into just 3 standard server racks. This isn't some room-sized cryogenic plant. It's a deployable piece of infrastructure. That is a massive leap in practicality. But this isn't just a story about clever engineering. The real answer to our mystery lies in the strategy, a deliberate plan to build an entire industrial ecosystem, not just a single perfect machine. This slide really shows the master plan. China recognized that relying on foreign parts, which are often subject to export controls, was a critical vulnerability. So they decided to build everything themselves, creating this incredibly fast, self-sufficient development cycle. This domestic control allowed them to create custom components perfectly suited for the task. Take their laser systems. It's a perfect example. They didn't just design their own, they made them consume just 1/10 the power of imported equivalents. That's a huge win for efficiency and cost. And they didn't stop at the hardware. They've built an entire software ecosystem on top of it, with a cloud platform and visual tools that shield users from the hardcore physics. It's designed to get engineers and researchers working on it today. So the crucial point is this. It's the combination of practical, accessible technology and a deliberate strategic ecosystem that has pushed China across the commercial finish line. The quantum race is no longer just about lab breakthroughs, it's about delivering real, usable products. And this brings us to the real-world impact. The Hanyuan one is not just for sale, it's being deployed, exported, and scaled. It's been delivered to a major telecom company, exported internationally, and is now the foundation for a planned quantum data center, turning this technology into a shared national resource. All of this leads to one final, provocative question that the entire tech world is now asking itself. Given this sudden shift from experimental physics to commercial engineering, has the West already fallen behind in the race that truly matters? Share what you think in the comments. And if you liked the video, subscribe, leave a like, comment on what you liked most, and share the video.